Okay, now we're going to see where all that goes, but let's establish another important idea, okay? Let's consider the similarity transformation T inverse AT. Now, if A is a diagonalizable matrix, not necessarily diagonal matrix, but diagonalizable, then it's diagonalizable by forming the column, a column matrix, a matrix with the eigenvectors of A as its columns, a square matrix with eigenvectors as a column, as the columns, and then multiply A by T inverse on the left and by T on the right, and you're going to get the diagonal matrix. So this is going to be T inverse AT is considered to be a diagonal matrix. Okay. Now, what do we get if we cube T inverse AT? Okay, well, one way of writing out what we get is T inverse AT times T inverse AT quantity squared. Okay? Well, let's see. Matrix multiplication is commutative. What I did there was really wrong and quite stupid. I squared this, but I didn't square the T inverse or the T, did I? Now, what I wrote here is actually true, but we haven't established it. So, what I want to write here, I want to change this. I want to see what T inverse AT squared is, okay? There's no reason to use the cube anyway. So, T inverse AT squared, you can accept that. It's T inverse AT multiplied by T inverse AT. Now, matrix multiplication is associative. It's not commutative. You can't change the order of these matrices, but you can group them any way you want. And this, I've got to get rid of those squares. Okay, so that this line actually says the same thing the first line does. And I've got to get rid of those exponent 2. And now I've kind of obliterated some of my writing, but we can fix that. Okay. Okay, now what I'm doing here is I've got a T next to T inverse, right? So there's no reason I can't multiply the A times the T, and then I'm going to have to multiply, I could then multiply the T by the T inverse and the T inverse by the A, or anything I want to do. But the point is, I can multiply that T times T inverse right now if I want to. And that's what I want to do. So I group the T inverse. Of course, T inverse is the inverse of T. When you multiply a matrix by its inverse, you get the identity. And then, well, I haven't written out the step, but I could have written the identity times A in parentheses, and the identity times A is just A, so A times the identity times A, and if you had linear algebra, you should understand that anyway. That's going to give you A times A. And of course, A times A is A squared. Now we're still left with the T inverse on this side and the T on this side. We haven't done anything with them. But now we have T inverse A squared T. So that when I square T inverse AT, I get T inverse A squared T. Okay? Now, in general then, we can extend this process. We can say that T inverse AT raised to the n is T inverse times A to the n times T. Well, actually that's not what we're saying. We can say if T inverse AT raised to the n is T inverse A to the n T, then it follows that T inverse AT to the n plus 1 is equal to T inverse A to the n plus 1t. In other words, if this sort of thing is true for the nth power, looking for the word, of T inverse AT, then it's true for the n plus 1 power. showing that if it's true for one power, it's always true for the next. Now, we just saw an argument of that nature, and we're seeing another one. We've shown that it's true for the second power, and if it's true for any power n, it's true for the power n plus 1. So if it's true for the second power, it's true for the third power. If it's true for the third power, it's true for the fourth power, and so forth. Well, that's the argument we want to make. We just have to work through the details of showing that this is equal to this. But those details are almost exactly the same as they were here. So if you understand what we did here, this is going to be really easy. So what do we say? If T inverse AT raised to the n is T inverse A to the NT, then T inverse AT to the n plus 1 is what? Well, it's T inverse AT multiplied by T inverse AT to the n. But if that's T inverse A to the NT, we can write this as T inverse AT times T inverse A to the NT. And now we can multiply the T and the T inverse to get the identity. So we have A times the identity times A to the n. Well, that's just A times A to the n, which is A to the n plus 1. So that proves that if this is true, then this is true. Okay? Then, yeah, well, that's it. This is a proof by mathematical induction. So, we can take any power now of T inverse AT, and it's just T inverse times the nth power, you know, whatever the power is, times T. Okay. Now, I'm going to save this for a little later, but let's look at then, and I don't know why I wrote that out, except that I'd written it out for the cube here. So I wrote it out for the square here, but I changed the cube to square, so I've already done that. So, you know, that's the same thing this is. Okay. Now we want to come back. Well, we want to look at the identity matrix plus our lambda 1t, lambda 2 matrix, plus the square of that matrix, plus the cube of that matrix, plus, etc., out to the nth power of that matrix. But dividing the second power of the matrix by 2 factorial, the third power by 3 factorial, and the nth power by n factorial. Well, that matches the formula, and I think I've already erased it, but for the exponential function. This is just what we get if we do the exponential of the matrix, okay? It's TA to the 0, which is the identity, TA to the 1, TA squared over 2 factorial, TA cubed over 3 factorial, okay? And it's unfortunate I'm saying TA because this is a TA and this was a TA, okay? So we're not talking about the matrix T now, we're talking about the variable T, the time variable, let's think of it, okay? So anyhow, this is how we would write out the Taylor series for the matrix TA, okay? So, we want to say e to the TA equals all this. Okay, it's TA to the 0 plus TA to the 1 plus TA squared over 2 factorial and so forth. Okay, so there are the first 3 terms and then the rest follows similarly. Okay, so if you write that out, there it is. And now what happens, what do we get if we add these up? Well, the first row, first column is going to be this, plus this, plus this, plus this. We just add up all the first row, first column quantities. And what are those quantities? Well, it's 1 plus lambda 1t plus lambda 1t quantity squared over 2 factorial and so forth forever. Okay? And our first row, second column, and second row, first column numbers in this diagonal are still going to all be 0, so they're going to add up to 0, so we're going to get zeros here. And then the second row, second column number is just going to be our numbers 1 plus lambda 2t plus lambda 2t quantity squared over 2 factorial, then plus lambda 2t quantity cubed over 3 factorial, and so forth out to lambda 2t to the n over n factorial and beyond. Well, okay, that's great, but what's this? This is just e to the lambda 1t. That's just a Taylor series for e to the lambda 1t. And this is just a Taylor series for e to the lambda 2t. So that the e to the ta matrix for a diagonal matrix, if the diagonal matrix is lambda 1t, lambda 2t, okay, just gives us e to the lambda 1t, e to the lambda 2t. Now that doesn't work if it's not a diagonal matrix, because the powers of other matrices are much more complicated than the powers of diagonal matrices. All the different elements interfere, and you don't have the simple result that you do for a diagonal matrix. Now, if the matrix A is not diagonal, if it's diagonalizable, then you would want to do this with e to the big T inverse A, big T, times the little t variable, but it would be very similar. Okay, so this is a plausibility argument. The other thing now we can say, and we tie this together next time, so I'm just giving you a little teaser here. Our typical, if we have the function y prime equals ky, how do we solve that? Well, it's separable, so it's easy to solve, but we can also solve it by just letting y equals a e to the rt, right? Or in general, a y prime equals py vector, okay? We want to try solving that by y equals a e to the rt. So what we want to do is we want to, for a system of equations, we want to see if we can solve a phi prime equals p phi by letting phi equal e to at for some matrix A, for some diagonal matrix A. Okay, and then we can proceed to find the matrix A. It only works phase diagonal, so we're going to have to diagonalize P before we can get to that. So we're going to see how that works out. But we know how to diagonalize a matrix. We now understand the exponential matrix. And we could also form the same thing is going to be true for a sine or a cosine. The sine of the AT matrix, if A is diagonal, would just be sine of lambda 1t, sine of lambda 2t, and so forth if your matrix is bigger. Cosine, same thing, okay? It all makes sense. Now to show that it really does make sense, let's verify that it at least obeys a product rule, a chain rule, okay? We want to verify that e to the ta prime, the derivative with respect to t of e to the ta, is equal to a times e to the ta, because that's exactly what you would expect if the chain rule applies. And I'm just checking time here. We're running a little short, but I think we can make it. Big penalty if I go over 15 minutes.